Hello and welcome. So recently we've been talking about doing inference when we have numerical data. In this lecture we're moving into a discussion of the analysis of categorical data. We're going to start with doing inference about a single proportion in a population. These are methods that are going to be useful when we have research questions about the proportion of observations that fall into a particular category or that have a particular trait or attitude or something like that. So I might want to estimate the proportion of adults in the United States who identify themselves as Republicans and also construct a confidence interval around that estimate. Or I might have a particular hypothesis that I want to test. For example, I might want to know specifically if more than 50% of people in the United States could find Iraq on a map. To get started here, I have a question for you to consider. So two scientists want to know if a particular drug is effective against high blood pressure. One of the scientists wants to give the drug to 1,000 people who have high blood pressure and see how many of them respond to the drug by experiencing lower blood pressure levels. The second scientist wants to give the drug to 500 people and not give the drug to another 500 people and see how many people in both groups experience lower blood pressure. So which is the better way to test this drug? The first scientist's way or the second scientist's way? So I hope that's a really easy question for you to answer. The key component of a good research design is that it allows us to make a comparison between groups. So in this case, we want to know if this medication is effective in combating high blood pressure. So we need to be able to compare people who took the drug to people who did not take the drug and see if people in those different groups experience different blood pressure levels that can be attributed to the effect of the blood pressure drug. So the correct answer is that 500 people should get the drug, 500 people should not. They should be in the control group so that we can compare those groups to one another. So the General Social Survey is this big survey in the United States that's used to find out the proportions of people in the US who fall into particular demographic categories or who have particular beliefs or attitudes or knowledge or something like that. So this question about research design in this blood pressure drug trial was asked in the 2010 General Social Survey, and 99 out of 670 respondents answered incorrectly that all 1,000 people should get the drug in order to do this trial, and 571 answered correctly that 500 people should get the drug and 500 people should not in order to compare these groups and understand whether the medication is effective. So we're going to use this survey data to answer a question that we have. We want to estimate the proportion of all Americans who have a good intuition about experimental design, and we're going to measure that by looking at the proportion of all Americans who would answer correctly that 500 people should get this drug and 500 people should not. So it's sort of our proxy measure for understanding how well Americans grasp the fundamental principles of comparison that underlie experimental design. So we have a parameter of interest and a point estimate that we need to talk about. Our parameter of interest is the proportion of all Americans in the population who have a good intuition about experimental design. We're going to denote that as P. And our point estimate is going to be the proportion of Americans in our sample who have a good intuition about experimental design, so who answer this question in the correct way. And we're going to denote that as P hat. The hat over the P, this little caret symbol, indicates that this is an estimate. It is a statistic from our sample, and we're using it as our point estimate for the population parameter P. So this is the same research setup that we have been dealing with for this entire class. We have data on a sample. We want to make inference to a population. We have a point estimate for the population parameter that we're interested in, but we know that our point estimate is just an estimate. There is variability around it. So we need to not only have the point estimate, we need to have some way of quantifying our uncertainty about that estimate. We want a measure of our confidence in that estimate. So we have this research question about the percent of Americans that have good intuition about experimental design. We have data on that from our sample from the General Social Survey, and we're going to construct a confidence interval around our point estimate. So of course a confidence interval always takes this generic form of the point estimate plus or minus a margin of error, and a margin of error is always equal to a critical value times the standard error of the point estimate. So the thing that we need to know right now is how we calculate the standard error in this particular situation. So when we're doing inference for a single proportion, how exactly do we calculate the standard error that we need to construct our confidence interval? So here's that formula for the standard error of a sample proportion. It's equal to the square root of p times 1 minus p over n. So n is our sample size, p is the proportion that we're interested in, and 1 minus p is 1 minus the proportion that we're interested in. So if the proportion is 0.75, 1 minus p is 0.25, you multiply those together, divide them by your sample size, take the square root, and that is your standard error. So earlier in this course, we have talked about how we estimate population means using samples. And one of the cool things about estimating means is that the sampling distribution of sample means is nearly normal under the right conditions, which means that we can use the normal approximation, which gives us some really cool statistical techniques that we can use, so it makes our lives easier when we're doing inference. Now, it's not true that every sample statistic has this property where the sampling distribution of the sample statistic is nearly normal. That's not the case for all sample statistics. It is true, though, for sample proportions. So the sampling distribution of sample proportions is nearly normal, with a mean that's equal to the true population proportion and this standard error, the square root of p times 1 minus p over n. So p hat is distributed this way. Of course, this is only going to be true under particular conditions, so let's go ahead and talk about those. So it shouldn't surprise you at all that one of these conditions is independence, that our observations in our sample be independent of one another. So the best way to ensure that is to take a good random sample from the population that you're interested in studying. The other condition is that there be at least 10 successes and 10 failures in our data. So don't get hung up on the language of success and failure. This is just terminology that we use to refer to this. We are interested in estimating the proportion of observations that fall into a particular category. So some of our observations are in this category, some of them are not. We want to make sure that we have at least 10 observations in our category of interest and at least 10 observations out of our category of interest. So in the example that we have been talking about, we're interested in the proportion of people in the American public who fall into this category of having good intuition about experimental design. We want to make sure that we have at least 10 people in that category who answered that survey question correctly, and at least 10 people in the category of people who did not answer the survey question correctly. So that's all that success and failure condition means. So let's go back to looking at this example that we've been talking about. So in the General Social Survey, we found that 571 out of the 670 people surveyed answered the question on experimental design correctly. So that's 85% or so. And we want to estimate, with a 95% confidence interval, the proportion of all Americans who have good intuition about experimental design based on this sample data. So we have a good size sample, an N of 670, and our estimate of this proportion is 0.85, so that's p hat. So the first thing that we should do is make sure that our conditions for inference are satisfied. So we just talked about these. The first of them is independence. So the General Social Survey takes a random sample from the American public, and the sample is not too big. It's less than 10% of all Americans, and so we're safe to assume that the independence condition is satisfied, that one respondent's answer to this question is independent of anyone else's. We also have this success-failure condition to think about, so we just want to make sure that we have 10 people in each of these categories, and we definitely do. We have 571 people who answered correctly and 99 people who answered incorrectly. Both of those are greater than 10. So our conditions are satisfied and we can move forward. So we have all of the data and the formulas that we need to go ahead and calculate our confidence interval. Remember, we're calculating a 95% confidence interval. So I've given you a couple of options here for how we would go ahead and calculate this. Take a minute and see if you can pick the right one. So the correct option is A. We have our point estimate, p hat, which is 0.85, plus or minus our margin of error. So we have our critical value, which is 1.96. Now this, of course, comes from the z-table. We're able to use the z-table, the normal probability table, because we can use the normal approximation for the sampling distribution of sample proportions. So our critical value for the 95% confidence interval in the z-table is 1.96. So we have that critical value times our standard error. And the standard error is p, which is, in this case, estimated using p hat, the sample proportion. So 0.85 times 1 minus p, which is 0.15, divided by our sample size, 670. Take the square root of that, and if we calculate that all out, we get a 95% confidence interval from 0.82 to 0.88. So that's how we find a confidence interval around our estimate of a sample proportion. The next thing that we're going to go over is doing a hypothesis test for hypotheses about sample proportions. But before we do that, I need to go over a couple differences between these types of calculations. So when we construct a confidence interval, we're using information from our sample to give us confidence bounds around our population estimate. Whereas when we do a hypothesis test, the whole idea is that we are comparing the data we observe to a hypothetical null distribution. So we're going to use some measures from the null hypothesis to do the test. So when we find a confidence interval, we use the number of successes and failures that we observe in our sample to make sure that our success-failure condition is met, that we have at least 10 observed successes and 10 observed failures. And when we calculate our standard error, we use p hat from our sample as p in the standard error formula. When we do a hypothesis test, we're going to calculate both of these things differently. So first, our success-failure condition means that we need to make sure that we have at least 10 expected successes and at least 10 expected failures under the null hypothesis. So what that means is that we use our sample size n times the proportion under the null hypothesis to find these, to see if the condition is satisfied. So let's say that our null hypothesis says that p is equal to 0.7, and we have a sample of 100. So then our expected number of successes is 0.7 times 100, which equals 70, and our expected number of failures is 0.3 times 100, which equals 30. So that's how we would make sure that this condition is satisfied in the hypothesis testing approach. When we calculate the standard error for a hypothesis test, we're going to use the null hypothesis value for p in our standard error formula. So let's go ahead and do a hypothesis test based on the example that we've just been talking about. So the General Social Survey finds that 571 out of 670, or 85% of Americans, answered this question about experimental design correctly. Let's say that we want to know whether these data provide convincing evidence that more than 80% of Americans have good intuition about experimental design. So our null hypothesis is that p, the proportion, is equal to 0.8, or 80%, and our alternative hypothesis is that p is greater than 0.8. So we have this normal distribution of the sampling distribution of sample proportions that's centered on our null value of 0.8, and we have our observed value of 0.85. So we're going to calculate our standard error as p times 1 minus p over our sample size, which gives us a standard error of 0.0154. So we're going to use this information to calculate our z-score. So we're going to take our observed proportion, which was 0.85, minus the proportion under the null hypothesis, which was 0.8, and divide that by the standard error that we just calculated, which gives us a z-score of 3.25. We can look that up in a z-table, or we can use R to find that that gives us a p-value of 0.0006. So remember, really small p-values give us reason to reject the null hypothesis. So in this case, we have convincing evidence that more than 80% of Americans have a good intuition about experimental design. So let's look at one more example really briefly. In a 2006 Gallup survey, 11% of 1,001 Americans surveyed answered that they had an objection to celebrating Halloween based on religious grounds. And at a 95% confidence level, the margin of error for the survey is plus or minus 3%. A news article reporting on this study says that more than 10% of all Americans have objections on religious grounds to celebrating Halloween. So I want to know, is this news piece's statement justified? So our 95% confidence interval goes from 11% minus 3% to 11% plus 3%, so between 8% and 14%. So what that means is that with 95% confidence, we estimate that between 8% and 14% of Americans have this objection to celebrating Halloween based on these religious concerns. So 10% is in the middle of this confidence interval. So the study tells us that the population parameter is between 8% and 14% with 95% confidence. The study doesn't tell us with any degree of confidence that the true population value is greater than 10%. It just gives us this interval where the population parameter is most likely to fall in. So this is a bit of a nuanced point, but it would be misleading to say that more than 10% of all Americans have this particular objection, because that's not exactly what the study is telling us. The study is giving us a good range of uncertainty around the point estimate of 11%, but the point estimate isn't the only important thing. We also need to take into account how wide the confidence interval is. So that has been our introduction to inference with single proportions. We are going to continue looking at categorical data in the next lecture, so I will see you then.